Assalamualaikum warahmatullahi wabarakatuh. My name is Ratna Kartikasari. I'm from Department of Mechanical Engineering, Industrial Technology Faculty, Institut Teknologi Nasional Yogyakarta, Indonesia. In this opportunity, I would like to present my paper with title Investigation the Effect of Soaking Time on Hardness and Corrosion Resistance of FeCrM and Alloy during Deep Cryogenic Treatment. Our recipients are Anita Susiana and Banu Rusman. The 300 series austenitic stainless steels, or what is known as 18-8 stainless steel, are widely used for cryogenic application because of high strength and toughness at low temperatures. FeCrM alloy occupies 65% of stainless steel application in industry. Unfortunately, this alloy is expensive because CrN and E is expensive. Various attempts have been made by world researchers to replace the nickel element, including the element of mangan. Recently, high-mangan austenitic steels have been developed for cryogenic applications in the natural gas industry liquid. That is inexpensive but comparable in strength, ductility, and toughness. FCC metal is widely used due to sufficient low temperature industry, but much effort has been directed to replace the alloy, and it still becomes an inexpensive high-mangan steel. Various treatments are carried out to improve the characteristic of this alloy, such as conventional heat treatment. Disadvantage of this treatment is residual stress and retained austenite. So, we develop cryogenic treatment, which is free internal stress, retained austenite, improve mechanical properties. This is due to all austenitic being transformed into martensite. Finally, dispersed carbide deposit and residual stress loss. Various studies have proven the effect of deep cryogenic treatment on various alloys, but the deep cryogenic treatment of Fe14Cr9.5 mangan alloys has not been specifically studied. This research aims to investigate the effect of soaking time on hardness, microstructure, and corrosion resistance. Chemical composition of FeCrM alloy is Cr 14.47 mangan 9.54 C0.09 Cu 1.13 Ni 0.81 Si 0.49 and P 0.03. The solid cylinder of the FeCrM alloy was cut using a bimetallic band saw blade to make the test specimen into microstructure and hardness test specimen. The corrosion specimen were made based on ASTM G30. The deep cryogenic treatment process was carried out in liquid nitrogen at a soaking time for 10, 15, 20, 25, and 30 minutes in GT nitrogen chamber. Then the warming process is carried out to room temperature. Microstructure testing was performed using an optical microscope Olympus metallurgical system microscope with a magnification of 200 times. Hardness testing used micro hardness tester using the Vickers hardness method with a load of 30 kilograms. Corrosion testing was carried out using the weight loss method in 3.5% NaCl medium. The result of this research is the first microstructure. The microstructure test result saw that the FeCrM alloy had an austenitic structure with a little varied between austenitic matrix. The austenite structure with clear green boundaries looks bright, while the varied structure looks darker. The high content of mangan element encourages the formation of the stable austenite structure. In contrast, a large amount of CR element as a ferrite stabilizer causes a ferrite structure to remain. Carbide deposits are seen among the austenitic structures, which have relatively homogeneous grain size. After 5 minutes of immersion, the number of ferrite structures increases while the austenitic structures appear smaller. At 10 minutes of immersion, the visible phenomena are the loss of the ferrite grains and dominant austenitic structure. At a longer immersion time, the austenite structure is increasingly visible with larger grains. It can be seen that the ferrite structure lamellas remain after 20 and 25 minutes of immersion. The carbide structure appears to be evenly distributed in small numbers in size. This phenomenon occurs in the raw material and after the density process for 15 minutes of immersions. At 20 and 25 minutes of immersions, carbides were seen to form lamellar glue-like patterns. The second is hardness. The hardness test results showed that the FeCrMn alloy had a hardness of 302.8 Vickers hardness. The density process with 5 minutes immersions showed a minimal increase in hardness, but this hardness continued to increase until 25 minutes immersions. A tiny increase in relatively fast immersion time is due to the absence of a crystal structure change, but with the longer the immersion time, the value of violence continues to increase. This is due to the arrangement of austenitic and carbide grains. A significant increase in hardness of 12.5% was obtained at 25 minutes of immersion with a hardness value of 340.6 Vickers hardness number. The increase in hardness is due to the emergence of secondary carbide formation with lamellar forms. The increase in hardness in the FeCrMn alloy is due to the emergence of secondary carbide with carbide formation with lamellar forms and large grains of austenite because the density process does not cause appearance of a mass transit structure. The last, corrosion resistance. Corrosion testing was carried out by using the weight loss method in a 3.5% NaCl solution. Corrosion test results show that the FeCrMn alloy has a corrosion rate of 0.026 mm per year. The high corrosion rate of FeCrMn alloys is due to the possibility that the forging process has been carried out after making FeCrMn alloys in cylindrical form. The forging process causes a smaller grain size and residual stress, thermal stress, which triggers a potential difference. The greater the stress is given to the material, the greater the potential difference resulting is a greater corrosion rate. The density process with immersion for 5 minutes causes FeCrMn alloys corrosion rate to decrease by 7.7% to 0.024 mm per year. This is because the density process encourages the growth of austenite grains and reduces the material residual stress. The conclusion of this research, the deep cryogenic treatment process of the Fe14Cr 9.5 Mn alloy changes the structure to austenite because secondary carbides to emerge and increasing the hardness and corrosion resistance. The authors would like to thank Ministry of Education and Culture of Indonesia to financially supporting this research by Hibah Penelitian Terapan 2020. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.